Let us look at proposition number 1 of works of Archimedes, specifically from measurement of circles. The proposition says the area of any circle is equal to a right-angled triangle in which one of the sides above the right angle is equal to the radius and the other to the circumference of the circle. So let's see how to prove this. Given a circle C with center O, given a triangle K such that S1 is equal to circumference of C and S2 is equal to radius of C. What the proposition is saying is that the area of this triangle is equal to the area of this circle. Now to prove this, we will use proof by contradiction. So which means we will assume that K is not equal to C. That means area of K is not equal to area of the circle. Okay, which means C is either greater than K or C is less than K. So which means we have two cases. So let's take it one by one. Case 1, C is greater than K. That means the area of the circle is greater than this triangle's area. Inscribe a square ABCD. So let's mark the points A, B, C, D. Bisect the arcs AB, BC, CD, and AD and construct the inscribed polygon. So we bisect AB at E. So when I say bisect AB, I'm talking of the arc AB and bisecting the arc AD. I'll restrict myself to only this part and the others follow the same logic. Again, bisect the halves repeatedly until the sides of the inscribed polygon, whose angular points are the points of division, subtend segments whose sum is less than the area of the circle minus area of the triangle. Because remember, we assume that the area of the circle is greater than this area. So the difference between these two areas, we are comparing these areas of these segments, which is left out of the square, with that difference. Now here, of course, these areas of these segments is greater than the difference between the areas of the circle and the triangle. So that is why we are bisecting it, so that we get a polygon which has more number of sides. So now if you notice, this area of the segment plus this, plus this, plus this, plus this, plus this, plus this, plus this. Again, we compare it with the difference between the area of the circle and this area of the triangle. If it is still greater, we again bisect these arcs and again construct an inscribed polygon which has more number of sides. So let's say this is where we stop. Let's say the sum of these areas of the segments of the circle is less than the difference between the area of the circle and the area of the triangle. A be any side of this inscribed polygon. Draw ON perpendicular to AE from O, and let's mark that as N. Now, ON is less than the radius of C, which means ON is less than S2. S2 is equal to the radius of the circle, and perimeter of the inscribed polygon is less than S1 because it is an inscribed polygon. So which means area of the inscribed polygon is less than the area of the triangle K, which is not possible since area of C is greater than area of K by assumption. So because of this impossibility, we can say area of C is not greater than area of K. So that is our first case. Now let's look at the second case, where we assume that the area of the circle C is less than the area of the triangle K. Circumscribe a square such that the adjacent sides of the square touches the circle at E, H and meet at T. And let it meet at T. Bisect the arcs between adjacent points of contact and draw tangents at the points of section. So bisect the arc. So let's bisect EH, the tangent. Let's mark F. Let's mark G. And let's join OG, EH, EA, AH, OE, and OH, and also OF. And let's join this as well. Let A be the midpoint of arc EAH. Again, bisect EA and AH. So now we bisected the arc EH. Now we bisect these two. I've actually done that. So here the points of intersection would be, so here I have bisected EA. Here I have bisected AH. So basically what we are doing is we are constricting the circumscribed polygon towards the circle. And we keep doing this till when? Till the difference between the circle and the circumscribed polygon becomes less than the difference between the area of the triangle and the area of the circle. Okay. Now we also draw OG perpendicular to AH, OF perpendicular to EA. Now, triangle TAG is a right angle triangle. TG, which is the hypotenuse, is greater than AG. Now, that means TG is also greater than GH, since AG is equal to GH. And triangle FTG is greater than half of the area TEAH. Means greater than half of the area TEAH has been cut off. Again, we bisect AH and draw a segment from OG and all that, so that triangle SGU is greater than half of the area GARH. So that means again greater than half of the area GARH has been cut off. Continuing this process around the circle, we get a polygon with more number of sides closer and closer to the circle. At some point, the area of the circumscribed polygon closest to the circle will be such that the area between it and the area of the circle C will be less than K minus C. Perpendicular from O to any of the side of the polygon is equal to S2 because it's equal to the radius of the circle. Perimeter of the polygon is greater than S1 because it is a circumscribed polygon. However close you take it to the circle by increasing the number of sides, the perimeter will always be greater than the circumference, which implies that area of C is not less than area of K. And since area of C is neither greater nor less than area of K, that means C is equal to K. So what we have done, we have shown that the area of a circle is equal to a right angled triangle whose one of the sides above the right angle is equal to the circumference of the circle and the other side is equal to the radius of the circle. So that is proposition number 1 of works of Archimedes, specifically measurement of a circle. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.